Okay, at this point, you should have all of this information about what forces are, what they look like, how we do some notation, what the types are, etc. Now we're actually going to go in the opposite way. That in general, in this class, you're going to be given a real-world situation, right? You're analyzing the world to try to model it with physics, do some mathematical calculations maybe, and really understand what's going on, analyze something, predict something. So we actually now need to go backwards. We need to look at a situation and identify the forces and figure out how to create the physics model. So here's our step-by-step method for doing this. The first step is to identify the object. Again, this is really important. Right now you only have one object. Later on, after we have the basics under our belt, we will be dealing with multiple objects, but before we have two objects, we'll have one object. So the first thing is to say, what is it that I want to study? What motion do I care about? What am I actually trying to figure out here? One object. Now again, your object can have multiple pieces. So an object could be my hand, or it could be my entire body, for instance. It could be a couch, or a person sitting on a couch, where that whole thing is one object. So the second thing to do is to draw a picture of the situation. And we haven't talked about free body diagrams yet. That will be coming in the next sequence, or two of videos. So right now you should at least just be drawing a picture. That's going to turn into a free body diagram, but it's still usually very helpful to have both. So visual representation, really important. Now there's one thing here that this says that I want to highlight, which is that touch it. So when you are showing your object and all other things going on, you want to think about what's touching it. And again, in general, we're only talking about contact forces, with the exception being gravity. Obviously, for gravity, we don't need to worry about it being a contact force. It's our only long-range force, but we're not even to naming the forces yet. We're still just drawing our picture. So make sure that you've identified everything that is touching it, and this will be important, especially for friction. So the next thing that this recommends is to draw a closed curve around the object. And the reason that it has you do this is we need to clearly separate what is our agents and what is our object. So we have one object which is inside of the curve, and all of our agents are outside of the curve. And again, you can actually have your agent be a composite object, like a laptop sitting on a desk, and that whole thing is one object, but that means that we're not thinking about how the laptop and the desk interact at that point, that neither of them are the agent. So that closed curve really helps you delineate the difference between object and agent, and I'll do two examples that show you what I mean. Next, you want to go back and now look at that closed curve and identify what is acting on it. So this goes back to 2, having that good picture. We need to think about these contact forces, and this is where the agents are touching our object. So now you've identified where there could be contact forces, and now we're actually naming and labeling them. Okay? There could be more than one. There's usually at least one. There's usually one. There could be more than one, especially like something pushing. There could also be friction. And try to use good notation. Again, if you have multiple forces of the same type, you need to add additional subscripts to make it clear which one's which. Finally, long-range forces. Toss that in. And again, gravity is normally what we're dealing with here. Normally, we don't have any other long-range forces, and you always want to consider this as a long-range force, since even if your object is not in contact with the ground, you can still have the gravitational force. So that's the process. And again, I'm going to do 2 examples, and this is really just leading in to doing free body diagrams, which we'll talk about very soon. So we have a bungee jumper here, and I'm sure this bungee jumper is having a great time. I, on the other hand, would not want to do this. So this bungee jumper is having a lot of fun, and so we want to go through and go step by step. So first step was identify the object. Here, it's the bungee jumper. That's whose motion we want to understand. So step 2 was draw a picture. So we have our bungee jumper, and there's then the bungee rope. Again, I don't know if the bungee rope really just attaches to the feet like this or some sort of whole body structure, because I would never do this, but that doesn't matter, we can simplify that. But we know that there's some sort of rope, in this case the bungee. Step 3 was draw a closed curve around the object. So here you go, you have your closed curve, and what this shows us is that our person is our object. And again, not just one hand of the person, not just the foot of the person, the whole person. Then we are going to look where the point where our agents, which are outside of the circle, touch our object. And in this case, you see, hey, there's this rope coming in. Now, here's an interesting point. Like I said, I'm not sure that this is actually how bungee jumping works. I would like to imagine there's some sort of whole body, like backpack rigging thing you're wearing. That wouldn't change this problem in any way, because that whole frame rigging backpack thing would still be part of your object, and the rope would still be coming in from the outside. So that's part of why we do it this way. There could be lots of details that we don't agree with. It doesn't matter. What matters is that there's an agent here, the bungee. Now, we need to name and label each contact force. In this case, because this is basically a rope, we just have tension. This is a tension force. And by calling it a tension force, we now know that it must be pointing in the direction of our bungee, right? Just by saying it's a tension force, we know what the direction is. Lastly, we say, hey, is there gravity? Yeah, so there's gravity. Gravity is going to be pulling down. So again, in this case, we're not going on to draw free body diagrams. That's going to be very soon, but just this first step is really important, since a common mistake is misidentifying forces, either saying forces are present when they are not, or by missing forces that are present. Second example is a little more complicated. Now we have a skier on a slope being pulled upwards. So there's a couple of different types of ski lifts. I don't know how many of you have much skiing experience. And while there's the sort of ski lift where you're hanging in the air, there's also another type of ski lift where you just grab onto a rope and it pulls you up a usually fairly short hill. So this is the situation we have here. We have a skier being pulled up a hill by a rope. So again, first, what is our object? This is where you have to know what you're trying to do, but let's say we're trying to understand the motion of the skier. So the skier is our object. So we draw a picture. We know that our skier, our person, is on some skis, which is probably on the ground, right? On some snow, and it's a hill. And then we have again our rope. Now, then, well, and actually, let me pause. You might be told something about the angle of the rope, right? That maybe the rope is perfectly parallel to the surface. Maybe it isn't. Maybe the rope is actually at a different angle, at an angle with respect to the surface. So that might be something you would want to include in your picture if that information was given in the situation. So then we draw a closed curve. Now again, this is important in that we need to say what is part of our object and what is not. If you draw the closed curve not including the skis, we would then think about the skis as an agent acting on our person. That's probably not what we want to do. We probably want to consider the skis as part of our object. So there you go. The skis are inside the curve. Next, we want to look at all of the points of contact. Now we again have a rope, so tension force. Nice. Now we look at what's going on down here. There is a normal force because our skis are resting on a surface, right? This is like the frog or the sled. We have a contact force here. We have one thing pushing on another. There's going to be a normal force. And again, worst case scenario, you later figure out that your normal force in this situation happens to be 0 for surprising reasons, but in this situation it won't be. There is a normal force. The second thing is that there's also going to be friction here if our skier is actively being pulled up the hill. If the skier was just sitting at rest, it would be static friction, but as the skier is being pulled up and is moving, we have kinetic friction. So on this surface here, you have two forces. So we've labeled them. And finally, yep, there's still gravity. Okay, gravity's still down. So there you go. So again, it might seem, you might think that you don't need to do this, but I really encourage you to try this approach initially, since where people frequently make mistakes with forces can really boil down to these 6 steps.